So maybe I should share my screen also. Yeah. Okay. So so yesterday and couple of classes. I mean, I think it's been about 10 classes. We've been looking at base nets. So I thought we'll move to some other topic. Probably it's getting a lot of base nets, a lot of probability. So today, and I think we have about 5, 6 classes. I mean, I don't want to take a class in the last week just before your exam because I think you need the time to internalize things. So I think we have maybe about 5 or 6 classes. So what I thought is I will do some things in ML, in machine learning formally, because today AI is like a lot of ML, right? So there were some of these concepts we saw. Like, I mean, of course, we have been doing things like RL, base nets, and these are all kind of allied with machine learning. But I thought maybe let's more formally get into machine learning, right? So so I think today, like all of you are, I mean, you probably have read about couple of machine learning techniques, but maybe let's more systematically go through things, because I think this is your first formal course in ML or AI in the institute. So we'll just get started to some concepts in machine learning, right? So it's a very vast field, and there are a couple of problems which come, couple of types of problems which come under the banner of machine learning. So we have seen some of them like in passing in some of the classes. So one of them is classification, right? And this is a problem where you're trying to, I mean, the essential idea in machine learning is to make predictions. Okay, so that's what at the bottom of it you're trying to do. You're trying to predict something about some data before actually that event happens. Okay, that's one way of thinking of it. So classification is one such instance where there are some features that are there. Okay, so maybe there are some features X, and there's some label given to each instance, so that we call as Y. Okay, so this is a tuple that's there, and what you want to do is you want to predict Y given X. Okay, so this is the setting in classification. So a lot of problems, right? Like detecting fraud transactions, for instance. So detect fraud transactions. So in this case, what happens is your X is a vector. So this is actually a vector which has like all the data relevant to the transaction, right? So maybe these are there's a credit card transactions, and maybe you have details of when the transaction happened, where it happened, what was the amount, and all such information. So that comes in the vector X, and Y is typically either +1 or -1. Okay, so this is 1 plus 1 if a fraud happened, if the transaction was a fraud, and -1 if it is not fraud. Right? So, these Ys are actually called, and sometimes you refer to it as classes, or sometimes you refer to it as labels. Right? So it's like labeling each instance. So X, this is called an instance. Okay, and you label each instance with a +1 or a -1. Right? So that's the setup in classification. And what you're trying to do is tomorrow maybe a new transaction happens, and you're trying to see whether it's actually fraud or not. Right? I mean, maybe it's the credit card company and there are reports that this was a fraud, but is it really fraud or not? You're trying to find that out. Okay, so this is an example. So there are many examples, right? Maybe you have some images, and maybe it's like some images of your cells, right? You want to detect whether it's a cancer cell or not. Okay, so it's a cancer, whether the person has cancer or not. So you have these images that the doctor has, and you want to see whether it's cancer or not. Okay, so that's one example. So this is in medicine, right? And there's so many examples out there. I think you probably will have, you would already be knowing a lot of such examples, right? So this is a very fundamental problem. So this is one type where your labels are discrete, so +1 or -1, and more generally, you can have, a set. So sometimes, you can have multiple classes, right? It's not, this is like a case where, this is binary classification, right? And more generally, you can have multi-class. So multi-class classification. So that is where the Y's can be something like, from 1 to up to K. Basically a discrete set. Okay. So in not just two classes, you have like multiple classes. So this could also be like maybe you have some images, some photos, and you want to see whether this is a photo of, scenery, or whether it's a photo of a building, right? Or something else, maybe photo of mountains, photos of rivers, things like that. So that is multi-class classification, where there are more than two classes. Okay, and there are other variants also. This is called, there's one label called multi-label classification. So where the Y can have like multiple values. So it's not just one of these. So Y, for example, and it could be that Y is something like 1 and 2. It belongs to both classes at the same time. Or it could be 1, 3, 5, something like this. Right? You could have multiple classes associated with each instance. Right? So that is what it's referred to as multi-label. Okay. And multi-class is just more than two classes, and but each instance is associated with only one class, that is multi-class. Okay, so yeah, more than two class labels, and but still each instance has only one. Each instance is associated with only one class. Each instance has only one label. Okay. So yeah, these are some of the different variants of classification, and so what we will do is, okay, we can't possibly go through all these variants. What we will do is we'll study some models for binary classification, and I'll just show you like how you can extend it to multi-class. We've already seen some things, right? We saw the name-based classifier. That all comes under classification. Okay. Now another paradigm is regression, right? So here what you want to predict is, it's again, you have these x and y, the instance is formed of these x and y values. So again, x is a vector, and the difference is that the y is a real value. So y is an element from the real number line. It's not a discrete value. So this is like the case where you wanted to, predict the, price of a house, how the price of a house changes with years. So maybe to predict the price of a house, or maybe the stock prices, right? Another possibility is that. Okay, so basically all these are real value. The price, all these prices are always, they take real values. It's not just, it's not a discrete value. So in that case, you call it regression, and there are different models. So actually, we've seen regression, right? When we did Q learning, what we did was we tried to model the Q value of each state action pair using some functions, and then we tried to learn that function, right? And so there the Q value was something in real. Okay, it was a real number, and we did regression there. Okay, so that's an example of how you use regression in reinforcement learning. Okay, so this is another paradigm. Now, one more paradigm we have is ranking, right? So in this is a slightly different problem. You can think of it as what happens when you search for something in Google search, right? You search for some query, and there are certain objects, set of objects that are returned to you. So it's a ranked order. So what you have is you have again x, maybe it's the query, and your y is actually going to be an ordering of various instances. So this is like an ordering of various objects, or even in your recommender systems, or like maybe when you purchase something in Amazon, right? You get a list. I mean, you purchase what you want, but it also shows you a set of other products that you might be interested in. And how does it decide what to show you first, and what is second, what is third, right? So it's actually doing a ranking. So there are algorithms for ranking as well. Okay, so this is another paradigm, and so we'll not go into ranking. Typically, what happens is, yeah, there are some algorithms specifically for ranking, But many times some algorithms that are there for classification can be adapted to ranking. So essentially, because you're trying to say whether an object is relevant or not, and maybe try to get some relevant score. So in that sense, you can also view it as a regression, but you can also, I mean, it's kind of like a combination of both. Okay, so that's about ranking. Now, yeah. So what happens typically is I mean, how do you actually learn this, right? What exactly are you trying to learn by doing this? In all these paradigms. So essentially, at the bottom of all this is, there's some function. Okay, or maybe let's just call it f. There's some function, which maps your features to y. Okay, so the x's, these are the features, your set of, whatever we saw as the small x, this vector. Okay, so that is the features, and this is like the class label, or in regression, this value of y, right? So this is also called the target sometimes in regression. Okay, so what you're trying to do in all these, the underlying principle is you want to learn a function which tells you that if I have this feature vector x, what is going to be my f of x. So the y is always going to be an f of x, and all of machine learning is built around trying to learn a function. Okay, and to do this, you're endowed with some data. Okay, and you're trying to somehow fit a function to the data, right? That's what you're trying to do. Now, so before we get into what are the kind of data sets and all that, um, you know okay, the space of functions, right, from x to y, that is a big collection, right? So if you don't make any assumptions, it's not going to be possible to zero in on some function, right? Because this is actually a huge set. You can have all possible values of assignments, all possible features. You can have different combinations, and you can have different assignments to each of these feature sets. Okay, so what you need to do is you need to make some assumptions, right, on the f, so that you restrict your space of functions. And so then what you do is you try to say that, okay, this is my assumption. I'll assume that the function has this form. And now what can I say? In this, assuming that the function is this form, what is the best value of that f can take? What's the best function that describes the data? Okay, so essentially what you're trying to assume is there is a bag edge, or this is called a hypothesis bag. Okay, so this is basically all your assumptions that you make about f, assumptions on f, right? So this is if I call let f, capital F, be the set of all functions, right? Set of all possible functions um, from x to y. If that's a big class, it's a huge set of functions. Now this h is going to be a subset of f, because you make some assumptions, because there's some more constraints that you're putting in on f. And so maybe something like this, your h is, this is your hypothesis bag, and there is a big space of all functions, right? And so this is capital F. Okay. Now, what you're going to do is you're going to try and find some function within this hypothesis bag, right? So the best function within this, so maybe some small h. That's what you're trying to find from here. Okay, and if your true function, there's some going to be some true function, and if that lies within h, that's pretty good. But otherwise, there'll be some errors, right? So there are a couple of aspects here. So this is what induces the concept of models, right? Why do we have why do we need to have different models? So the reason is this: based on what assumptions you make on the function, you can define different kind of models. For example, we saw naive Bayes, right? So naive Bayes was an example of a classifier where you use, the model was a Bayes net. So the underlying model was a Bayes net, and you had some probabilistic notion. So in terms of this function, defining what exactly you're trying to capture with the class labels, what you said is, we said we are going to have something like this. There's a true class, and there are different features, x1 up to xd. Okay, so these are the different features, and we said that there is a probability of each of these features given the class label, right? And so this was a simplifying assumption that we made, that all these features are independently generated given the class label. And then finally, what we said is, okay, somebody
Excuse
has a
me, ma'am.
question. Yes, Rishabh.
Ma'am, please explain the ranking once again. Means I do not get completely.
Okay, so
Means
ranking. So
basically, I want to know the what is the motto of the ranking.
okay. So in ranking, what you're trying to do is I mean, think of it in terms of what happens when you search for something in Google, right? You give a query. There are a possible set of pages that you can list out. Okay, and maybe you want to list the top 10 pages, right? So you want to list the top 10 pages and you want to have a ranking. So the first page that is listed is like the most relevant, right? And the second page is maybe not as much relevant, so it's a little less relevant, and so on. So the 10th page that you listed is still relevant, but it is the least relevant out of these 10, right? So what ranking is trying to do is, you want to come up with this list for each instance you take, for each maybe it's a query, and maybe it's a collection of all. So maybe let me just write it this way. So maybe it's a query word that you're trying to search for, and there is a set of all pages, right, that is available for with Google, right? And based on this, you want to come up with the list of this ranking. It's a ranked order of some top 10 pages, right? So it selects a few pages from this set and lists the best in some order. So that's what is ranking. So basically, any kind of retrieval task where you want to see like which is, what something is more important than the other, right? So it doesn't have a class label as such, but within the instances, so these pages itself form the instances, and within that you're trying to get an ordering, right? So that's what we mean by ranking. Rishabh, is the notion clear?
Yes, ma'am. So basically, ma'am, means for each instant we have the priority of the pages. That is the
Yes,
ranking.
yes, exactly, right?
Ma'am, so
Okay.
won't ranking be a part of regression? Like, can't it be considered a part of regression because we are like assigning a value to each y and then sorting based on that value?
Yeah, so that is one way you could do it. So give a score for each of the pages and then do a ranking. So you can do ranking using regression. And sometimes people also do ranking with classification, right? So maybe you have these values 1 to 10 assigned to, I mean, you want to assign 1 to 10 for each of the pages, maybe. Maybe it's like a fixed set of pages. You're going to list, I mean, there are only 10 pages in your collection, and maybe you want to give a value 1 to 10 to each page. That's also one way that people do it. Okay, so in that sense, it's not, you cannot call it an exclusive, paradigm as such, because many of the methods make use of either regression or classification or some combination of these to solve the ranking problem. But it's a class of problems which is there, and it's also well studied, right? Sometimes people use, I mean, there are different models again here for ranking. Right, but you're right. I mean, you can view it as a regression if you're thinking of it as code functions, or you could look at it as another variant of classification. But the essential thing is you want some kind of a permutation of these objects. That's the ultimate result you get. Is it clear,
Yes, ma'am.
Advait?
Got it.
Good. So you've all seen these kind of problems. I mean, you might not have studied it, but you have encountered this when you do some kind of a search. Uh, and yeah, all of these you would have encountered at some point. We're just trying to put it more formally down. Okay. Um, yeah. So yeah. So coming. So are there any more questions? Any other thoughts, questions? Okay. Okay, so I guess this is kind of clear. So coming to models, yeah. So what we were saying is, for any of these problems, you have to make some kind of assumptions. Otherwise, it's not possible to zero in on some function that you ultimately learn. Okay. So for that, what you have is some assumptions on your function that you're going to learn. So in the naive Bayes classifier, what we had was a base net. The assumption was that there is an underlying base net, and we had a particular structure for the base net. And what you were trying to do is you had some data, and with that you were trying to learn, there were some parameters. Okay, so the naive Bayes model had some parameters, and you were trying to learn that. Okay, so and finally you had a way of making predictions. So what you would do is you would learn parameters and use the parameters learned to make predictions. Use the parameters to make predictions. Okay. So this is more generally, this is what most models will do. You will have some assumption and there'll be some parameters which define your assumptions or which define the model. And you will learn it with some data. And then you use these parameters which are learned to make predictions. So in the case of naive Bayes, what you did was you learned all these parameters, probability of xi given ci, cj maybe, for different classes. And finally, for a new test instance, you had the x1, xd values. And then what you were trying to do is you would try to find the probability of cj given x1 to xd. And whichever maximizes it, you would try to take that. So you would try to find the class, so argmax of P of Cj, which is a class which is maximizing this probability, and you would report that. So the class reported was, so what you would say was y, your prediction was y hat is this, right? For this test instance, your y hat is going to be this. So that's how the procedure kind of went through. Okay. And yeah, so now what was going to happen was you had there would be a training set. Okay. I'm making a lot of spelling mistakes today, strangely. Maybe not strangely, I do that quite often. Okay, so there's a training set. Okay. You're probably seeing this in your lab assignment because there's a training set that's given to you. And, so this is basically a set with, x and y values, right? So this is a vector. So this is x1 to xd. And the corresponding y's. Okay, so maybe let me call it like this, xi, yi. So I is the particular instance. And maybe there are some n training instances. So I is from maybe the set 1 to n, but n training instances. So what this is telling you is for this instance, for this set of features, this is the label. So somebody is already telling you this. And now you have to get these parameters. So that's what you did. So that was the training set. Now there's another set called the test set. Okay. So here what happens is it has the same form. So D test, it also has these kind of pairs. So it will have xi, yi for a different collection. So maybe I is you have some m some m test instances. So what happens is here you're not going to use this to learn the parameters. So don't use D test. So what you do is you don't use D test for learning the parameters. But instead, what you will do is finally you will report, how well your model does on the test data, right? So then you will see, you will make predictions on the test data, and you will see how well it compares with yi. I mean, this is going to be the true label. Okay, you will see that, and what you will see is, what you will report is the performance on the test data. So what do we mean by performance? So there's some notion of loss functions. Okay. So that's what you're going to report, loss functions, or it's also called error. Okay. So what you will do is you will get a prediction. So for each instance in the test set, you will get a value of y hat, and you will compare it with the true value yi. And maybe you will take a sum over all the instances. So y hat I is there, so that's for the ith instance. And there'll be some kind of a loss function, and this is what you will report. So this is the total loss. Okay. This is what you will report, and this is for I in 1 to n. So this is only for the test set. You will report this. Okay, so the important thing is this is not something that you will use for training. You will train with this 1D train, and based on whatever parameters. So this will give you a list of parameters, and those parameters you will use to make predictions on the test, and you will report the loss on the test set. Okay, and you can do this with various models, and then maybe you pick the one that's best. Okay, so that's how the whole procedure works. Okay, so yeah, so one model that we've seen for classification is naive Bayes. Okay, now I also want to look at another model which has a slightly different, which makes slightly different assumptions. So the naive Bayes model is this is actually a probabilistic model, right? Because what we are essentially seeing is what's the probability of a class label given the instances. And everything is in terms of probabilities, and we're trying to find the best, okay, and maximize this probability. That's what you're trying to do. Okay, and even you'll probably see it next time in your machine learning class. This process of learning the parameters, right? So how did we do it in naive Bayes? We basically said that xi given cj. So we basically did a count of your entire data set. You saw how many times xi, a particular value of xi, occurred with cj. Okay, and then you divided it by the total number of times the class cj occurred. This is small cg. Okay, so this is how you computed these probabilities, and maybe you had some way of adding some you wanted to avoid these probabilities taking a value of 0, right? So what we said is you can add a 1 here. So maybe let me just write it separately. So a modification that you did was something like this, right? Xi given Cj equal to this. What you did is you counted the number of times Xi occurred with Cj, and then there was one variant where you add a 1 to the numerator, and the number of times Cj occurred plus the number of possible values that this feature Xi can take, right? So this is basically the number of possible values, that that xi can take, that the feature xi can take. Okay? So of course this works with discrete, assuming your features are discrete, the discrete value. So this was one way of computing these probabilities to ensure that you don't get extreme values of the features. Okay, you don't get the extreme values of parameters. So this is called Laplace smoothing. And effectively what it's doing is if you didn't use it, if you use this probability computation without this +1 by number of x's, maybe it would have really done well on the training set. Okay, you can measure your loss even for the training set. So maybe that loss would be minimal if you went with this approach, but you're not guaranteed for the test set. Okay, so because in the test set you can have more generally for any other instance that you don't train with, you can still have this value of xi and cg. But your learned model, if you don't account for these counts, these +1 and xi's, the size of xi, what's going to happen is this probability will become 0, and that will make your entire probability 0 in some sense. So this entire probability ends up becoming 0. So okay, so why am I telling you all this? So this was a way in which you were trying to generalize your model. So you're trying to learn a model with a training set, but always you should ensure that, your ultimate goal is to do well on some unseen examples. The training set is just a way to enable you to do this learning, but you should also not get an error, or the loss or error on the training set should not be like 0. Okay, because that indicates there's a problem, that it's like fitting too well for the training set, but for the test set things might go very bad. Okay, so this is actually a way to avoid overfitting. Okay, so the technical term for this phenomenon where you do very well with the training set, but on the test set things go bad, right? So that phenomenon is called overfitting. So anyway, we'll see this more, as we do some of these models. Okay. So this was just a quick recap on naive-Bayes classification. Now, I want to just start off with another model, which is called the perceptron. Okay, so this is a slightly different kind of model. It's not a probabilistic model. So this is actually a linear classifier. Okay, so what does it mean? We'll see. So now before we do perceptron, I just want to do some recap of some concepts on vectors, dot product, and hyperplanes, because that is something that the perceptron is going to use a lot. Okay, so let's just do some recap. So recap on vectors, inner products. Okay. So this is basically stuff that you've already learned in your maybe your 12th standard. It's starting from then, but I just want to touch upon some of the things which are most useful for the perceptron algorithm. Okay, so what is a vector? You all seen vectors. So maybe in space you represent it like this with array, and this it has a magnitude and there's some direction, and you always take it with respect to the coordinates, right? So if you have x1 and x2 axis, this is a an example of a vector where there's a it's a direction and also some magnitude. Okay. And you typically write a vector as how much it measures out in each of these directions. So if this is a value x1 and this is a value small x2, this vector would be denoted like this, x1, x2. Right? Now, I'll just write the endpoint. So this is the origin. It's always measured with respect to, it's relative to the origin. And this endpoint may be A. So the different ways you can write A as a point, and you can say it is x1, x2, or you can think of it as a vector OA. Okay. Now, these vectors, I mean, though we always say that there's one endpoint, which is the origin, typically you can also write the same vector, in a slightly displaced way. Okay, so this is actually the same vector. So it's as though you're moving the coordinates. So if you move your origin to somewhere here, okay, so this would be x1, x2 with respect to that coordinate. So in that sense, the vector, this is also the vector OA itself, but in a slightly displaced. Okay, so generally when we say a vector, you can draw it in different parts of the space, right? The vector OA, you can draw it in different parts of the space. Okay, so that's about just an introduction to vectors. Now, how do you add two vectors, right? So suppose you had, there's a vector like this. So this was x1, x2. Okay, and maybe let me call, yeah, okay, x1, x2 is fine. And maybe there is another vector y1, y2. Okay, and now I want to add these two vectors. So we all know the parallelogram law. So what you will have is, then you have a new vector like this. This is going to be x1 plus y1 and x2 plus y2. Right? So this is the new vector. And how did you get that? You moved this vector y1, y2 a bit away. You displaced it here. So this was also the same vector. And you could add, okay, so the new coordinates were obtained by, so x1, x2, and this was actually the, it's the same vector y1 plus y2, and then you could add them. Okay, so this is how you added two vectors, right? And yeah, and then we also have this notion of inner products, right? So if you have x1, x2, and y1, y2, right? So these are these two vectors, x1, x2, and maybe y1, y2. Let me draw it like this. Right? So what is the inner product between x and y? So this is a vector x and this is a vector, sorry, this is y and this is x. So what is the inner product between x and y? How do you define that? This is all something you've seen, right? So I just want you to just get interactive and we can discuss this. So x dot y, right? How do we write this?
x1 y1 plus x2 y2.
Yeah, x1 y1 plus x2 y2. So you take each coordinate, you multiply it, and then sum them up. And other way of writing this is the magnitude of x times the magnitude of y, and there's an angle that these two vectors make with each other. And this is also another way. This is also something that you would have seen, right? And the magnitude of x, so this is a Euclidean space. So the magnitude of x is always written like this. We write it this way. So square root of this, right? So these are two different ways in which you write the inner product, and both these are equal. Okay, and more generally, if you have like higher dimensions, you would write this as x, I mean the sum of all these products. Okay, all right, so I mean you should be able to see why this is true using some trigonometric identities. You can prove why this holds. Okay, and so yeah, so when do we say that x dot y, or this is also x transpose y if you use the vector notation, because x you will write it as x1 to xd. So it's a column vector, and this transpose y1 to yd, right? So this is how you write the inner product. And yeah, so when do we say x transpose y? How can we say that this is greater than 0? Right? So when do we say that this is a value greater than 0? And to analyze this definition is what helps. This way of defining the inner product is what helps. So these values, the norm of x and norm y, these are always going to be greater than 0. So norm x and norm y, so these are all magnitudes. These are going to be always greater than 0 from here. Okay, and cos theta is a value which it lies between -1 to 1. Right? So if x transpose y is greater than 0, uh, when does that happen in terms of the angle theta?
Minus 92%.
Say that again. I couldn't hear you. Can you just repeat that?
Minus pi by 2 to pi by 2.
Minus pi by 2 to pi by 2, yes. So so effectively what that means is, you have, so this is everything which is pi by 2 at an angle orthogonal to x, that's the term. And anything, so if you take y here or y here, right, all these are going to make an acute angle, right? So that's between minus pi by 2 and pi by 2. And so those, for all those cases, you will have x transpose y as greater than 0. So this angle should be an acute angle, basically. Okay. And the moment you have y somewhere in this path, right? So for x transpose y, if it is less than 0, that means that the orientations are like this. So x is here, and your y is somewhere here in this part. Okay, in this part of, on the left side of this line, basically. Okay, so this angle is going to be obtuse. So in that case, we'll have x transpose y as less than equal to 0. Okay, so these are some things, it's just a recap of these concepts because these are going to be useful for the perceptron algorithm. Now, a final thing I want to do is the concept of lines and planes. Okay, so let's just look at lines, or generally what we want to see is hyperplanes, which is a generalization of a line. So let's just take a two-dimensional case. So suppose I take this line. So there's a line passing through the origin. Okay, there's a line passing through the origin, and maybe let me say that this is a line which is like y equal to minus x. So this is the y-axis and this is the x-axis. Okay, so yeah, this I can also write it as x plus y is 0. Okay, and more generally what we have here, so y equal to minus x in the case of two dimensions, what we have is y equal to mx plus c, right? So m is like the slope of the line, right? So in this case, it has a negative slope, right? So the slope here is -1, and c is like an intercept, right? And here the intercept is 0, it's passing through the origin. right? So this is the equation of this line. Now, this is something that you would have seen. And so how do we generalize this concept of lines to higher dimensions, right? So in the case of 2 dimensions, we have this notions of slope, which is like really well defined. But in a higher dimension, so suppose you have 3 dimensions, what you need is the concept of a plane, right? So something like this, right? So how do we define slopes then? There's no concept of a slope as such. So what happens is in higher dimensions, the equation of a plane or a hyperplane, as it's called, would be something like this. You'll have w1 x1 plus so on plus wd xd equal to 0. Okay, so that's the equation of a hyperplane. So let's see where that comes from. So one way in, let's come back to this 2-dimensional example. So one is y is mx plus c, that's something we have. Now another way to look at this, y equal to minus x, is to say that, this line consists of all points which are orthogonal to this vector 1, 1. Okay, so this is a value 1 and this is 1. Okay, so if I take any point, so let's take maybe a point here, okay, or somewhere here maybe. So this is the point which is like minus 2 and 2, right? So the x coordinate is minus 2 and the y coordinate is 2, right? So if you take the inner product, right? So minus 2 and 2, if you take the inner product with 1, 1, what do you get? What is it going to be?
0, ma'am.
0, right? So what's happening is if you take minus 2, so this vector minus 2, 2 is essentially this vector, right? And that is orthogonal to 1, 1. Okay. Now any other line, any other point or any other vector you take on this, any other point on this line, so that amounts to a vector like this. So if you take a point here, it amounts to the vector OP, right? So the point P is also represented as the vector OP. So it makes a 90-degree with this vector 1, 1. Okay, so that's the case for every point on this line. Okay, so let's take maybe even something here, right? So maybe you have like the x is 0.5 and y is minus 0.5. So even for this, if you take its dot product with the vector 1, 1, you're going to get 0. Right? So more generally, there is a vector w. So this is some vector w, and it makes a 90-degree with everything on this line, every point on this line, right? So this idea is something which generalizes to higher dimensions. So there is going to be some vector which is orthogonal to this plane, and that vector is w1 to wd. Okay, and it makes a 90-degree, or it's orthogonal to every vector x1 to xd on this plane, right? So that's the idea. So yeah, if you have 3 dimensions, it's like, I don't know if you can see. Yeah, so what happens is, if this is the plane, there's going to be this kind of a vector, right, which is it's like popping out from this plane. So every point on this book is going to be orthogonal to this pen, right? So it's just that concept. So that's the vector w. So that's the vector view of a line or a hyperplane. Okay. Now what else do I want to tell you? Yeah, so another view again about these inner products, right? So W transpose X being greater than 0 or less than 0, right? So yeah, maybe, okay, so let's just do it with this part itself. Yeah, okay, so what we saw was a line passing through the origin, and similarly a hyperplane which goes through the origin. So now more generally, if you have something like this, a line which doesn't go through the origin, right? So then what happens is, again, there is this vector which is orthogonal, right? And this is orthogonal to every point on this line or every point on this plane. Okay, so it's 2 dimensions, so we'll just say it's a line. So W is orthogonal to every point on this line. And what that means is, if you take a vector like this, right? So let me call this point A and this is a point B. So then what it means is W transpose AB, the vector AB is going to be 0 always. Okay. And so in terms of point representation, if you take, so this is going to be the point OB, right? So, and A is this point OA, right? So A is the point OA and B is the point OB. Okay. Now, this OB, right? The way we added two vectors, this OB vector is just going to be OA plus AB, right? So it's just the sum of these two vectors, A and OA and AB, right? Now, if you try to take a W transpose on both sides, you multiply, you take an inner product with W for both these, on both sides of this line, on both sides of this equation, what you're going to get is W transpose OB is W transpose OA plus W transpose AB, right? So this is something that you're going to get, right? Now, what do we know about W transpose AB?
It's equal to 0.
Is equal to 0, right? And so what we are going to get is the inner product of W with OB and OA, or more generally, any point you take, it makes the same inner product with W, right? Any point on this line, if you take, it's going to make the same inner product with W. And so that's how you get this equation. W transpose X is sum B, right? So that's the equation of this line. So this is the set of all points such that W transpose X equal to B. And this is the equation of the hyperplane more generally. So this is how you define the hyperplane. Okay. All right. So now one more concept I want to just take is if you take some point here, okay. So suppose a point which is not on this line, right? Something over here. And so the point is something like this. So this is a point C. So now if I try to find W transpose OC, right? So visually, what do you think it's going to be? Is it going to be greater than 0, less than 0? What is it going to be? What's going to happen here? Is this greater than 0, less than 0? So OC is this
Should be
vector.
greater than 0.
Yeah, it will be greater than 0, right? Actually, it will be strictly greater than 0, right? Because what it's doing is if you can move this vector W here and it's making a positive angle with, it's making an acute angle with W, right? And you can actually prove it more formally because we can decompose OC as maybe a point here, right? Like OC, you can write it as a point on this line. So maybe something like this, OP plus PC, right? So that's how you can write, you can decompose OC. And P is a point on the line. So P is a point on the hyperplane. Okay. And what happens? So, okay, I think I wanted to just say whether it's greater than B. Okay, so if this W transpose X equal to B and B is greater than 0, this is going to be greater than B. Okay, so how do we know that? It's because, you can take W transpose on both sides. You can multiply both sides with W, take the inner product of both sides with W. Then what you're going to get is W transpose OC is W transpose OP plus W transpose PC, right? And what we know is W transpose OP, right? So this point P is here, and W transpose OP equal to value B plus W transpose PC, and this value is going to be greater than 0. That's visually because it makes an acute angle. And so what you're going to get is this is actually going to be greater than B. So W transpose OC is going to be greater than B. Okay. So of course, like here for this particular example, you'll have that it's greater than 0 itself. Okay. So essentially what's going to happen is if you take a point on this side of the hyperplane, so this is the hyperplane, and if you take something on this part, so this entire region, if you take, for those points, if you take the inner product with W, you're going to get a value greater than B. Okay, so more generally, this is going to be greater than B. Okay, and if you take some point on this side, so maybe something here, here you're going to get the W transpose X is going to be less than B. Okay, so that's also not too hard. By the same idea, you can try to see what happens. This value W transpose PC will take a value less than 0 if you take a point here. Okay, so this region as W transpose X less than B, and here you'll have W transpose X greater than B for every X in this. So these are actually called half spaces. So because there are two paths, right? This line is going to divide the entire space into two parts. So these are called half spaces. All right. So any questions so far? I mean, these are all simple things. I just want to remind you of these so that it helps the next discussion. Any questions so far?
No, ma'am.
Okay. So I think we are running out of time. So I don't know whether I should really do the perceptron algorithm today or okay. So maybe let me just give you some more ideas about the perceptron. So using these ideas of these lines or planes, you can actually build classifiers. Okay. So remember that all that we have is the features. So coming back to classifiers, so what we have is something like this, X and Y, right? So this is the set of features, and you have these as the labels. Okay? So what the perceptron is trying to do is it's trying to construct this kind of a line, okay, which separates out both the classes. So maybe your data is something like this. You have, so these are like the positive class. One class is like this. So for all these examples, maybe you have y is +1, okay? And maybe you have another bunch of examples here. Okay, so these are called the negative examples. So for all these, you have y is -1. So what the perceptron is trying to do is it's trying to build some kind of a line here which separates these two out. Okay, so essentially what you get is you're trying to find this vector W. Okay, and if W transpose X is greater than 0, so maybe your W is something like this. Okay, so W, maybe it's like, you write it with red itself. So W may, if this is the vector W, what you're trying to say is if W transpose X is greater than 0 for any instance X, I will say Y is +1 for such an X. And if W transpose X is less than 0, then I will say that Y is -1. Okay? So that's the underlying assumption for the perceptron algorithm. That's the model. Okay, and so the whole process is about finding the best vector W, right, which describes your training data. Okay, so yeah, so I'll just stop here for today, and we'll do the perceptron algorithm more formally in the next class. Okay, so yeah, thanks everybody. I'll hang back if there are any questions. Otherwise, thanks.